So what is electropolishing all about? Well, let's have a look at some examples and then you'll see and you will immediately know what electropolishing is in fact all about. So the idea behind electropolishing is to give a finish which is very, very shiny, what we call a mirror finish. So if you want an object to be very reflective, a very good example shown on the left-hand side here. This is a light fitting for a vehicle, which would normally have a headlamp bulb fitted here. And it's designed to have a mirror finish, and has a particular profile. They're either elliptical or they are parabolic, depending on what kind of light beam you want. So you want a mirror finish as opposed to just a normal regular finish like you might get with electroplating. Then you have to use a technique known as electropolishing to give this mirror finish. A very good example would be the knives and forks you eat with and spoons and so on. Often these are made out of stainless steel. Stainless steel on its own isn't good enough. You wouldn't want to use a stainless steel object like this that had not been electropolished beforehand. So it's a very nice, smooth, clean, clear, shiny surface. And this is done by a process known as electropolishing. So you get the idea. If you were to look under an electron microscope at high magnification at an object which has been electropolished, and you look on the left-hand side, the before surface, and on the right-hand side, the after surface, you can see it's the same object, but it's been changed significantly. First of all, it's not as thick. If you look at the wall thickness here, it's clearly thicker than the corresponding wall thickness here, which is much thinner. And also, this is a rough surface, especially you can see on the inside of the object. It's like a honeycomb, in fact. But if you look at the surface finish of the object after it's been electropolished, it's smooth. So electropolishing takes an object, and it doesn't matter what the shape is. In this particular case, it's some kind of honeycomb. And two things happen. One is you remove material, so you're dissolving the surface. And the second thing that's happening is you're making the surface very smooth and in fact shiny. And if you do it right, it should have a mirror finish. So the mirror finish is what we want, but the way we do it requires to remove material. So therefore, this is going to be a process where we need to take away material in order to create a smooth surface. So the question is, how do we do that? Well, first of all, the method we use is called electropolishing here. So the fact that we've got the word electro here implies, therefore, that electricity is involved, and the polishing is obvious. We're giving it a shiny surface. Let's look at this picture here. This shows 3 stages of electropolishing. On the left-hand side, we have a rough object. It's actually a pipe that's being cut away to give you an image of the inside of the pipe. Otherwise, you wouldn't see anything very much. And the inside is what we're interested in electropolishing, actually not the outside, but the inside. So this is the object as received before we've done anything. Over on the right-hand side, we have the object after it's been completely electropolished. And you can see it clearly has a shiny surface. You can see a reflection in it. And the one in the middle is somewhere halfway between. It's neither shiny nor rough. It's a surface somewhere in between this and this. So that's what we're aiming for. Here's another example. Electropolishing is often used in the food industry in order to prevent the metal, especially stainless steel, from actually dissolving in the food and giving it a bad taste, and also to prevent corrosion. Because the whole point about the corrosion protection with electropolishing is that because it has a very smooth surface, it means there are very, very few defects in the surface which can start to form pits and therefore give rise to pitting corrosion, which, as you know, is the main problem with stainless steel. So if you do the electropolishing correctly, then you get a perfect passive film form with very few defects in it. And it will therefore last for many years in service life, especially in the food industry, where you might want to have your plant in operation for 10 or 20 or more years without having to do any maintenance on it. And often we're polishing only on the inside of the container, not necessarily the outside. In this case, you can see it's both, it's actually on the outside in this particular case. So these are just examples of electropolishing. You'll find many examples if you look carefully enough. So what we need to do now is to understand a little bit about what's going on. Well, it is an electrochemical process. That's the first thing to understand. And unlike electroplating, we're almost doing the exact opposite of electroplating, because in electropolishing, the object that we want to actually polish is the anode. Whereas, if you recall back, for electroplating, the opposite is true. The cathode is always the object we're going to plate onto. But in electropolishing, we're doing pretty much the exact opposite. We're taking metal away by dissolving it away. So therefore, it should be obvious that the object being electropolished must be the positive electrode and is therefore the anode, what is called the work part shown here. And the cathode is the counter electrode, which could be made actually almost of anything. Very often we use stainless steel, actually, or we use graphite or carbon. And we can use other metals as well. It doesn't really matter. You could use platinum if you wanted to, but that's quite expensive. And they need some kind of electrolyte. And I'll say more about the electrolyte in a few minutes. But the basic process is we have a rough surface. And what we do is that this is for any metal. So we say Me is just a metal. It could be any metal. It could be iron in stainless steel, for example. And what we do is we make the atoms on the surface dissolve away, and they form M+ cations. And we need an opposite reaction to happen. So the opposite reactions we have is either hydrogen evolution, where for example, if this is an acid bath, which it might well be, I'll show you one later on made of sulfuric acid. But if this is an acid bath, then we've got a lot of protons. And therefore, hydrogen evolution is quite commonly the reaction that occurs on the cathode. And the anodic reaction will be this one here, where M forms M+. Sometimes we get oxide ions which form oxygen. So this is another counter reaction that could happen, in which case it would happen on the anode. And sometimes the formation of an oxygen actually can affect the surface properties or the surface quality of the electropolished surface. So we need to know if this reaction is happening or not. This reaction always takes place on the cathode, so it doesn't interfere with the polishing process on the anode, but this one can do. And the main reaction we want is the metal, Me, going to form metal ions. In this case, it's a cation since it's a plus ion. Over here on the right-hand side, we see a sort of artist's impression, if you like, a schematic drawing of what's actually going on. So if we go back to the photograph I showed here, the problem we've got to start with is we have a rough surface. You have bits of metal sticking out like mountains, if you like. If you imagine the cross-section as being like a mountain range, and we stylize that in our artistic diagram, we have this effect here. So the surface sometimes has holes in it or pits where the surface goes down. In other places, it sticks up like a mountain here. So this is the definition of a rough surface. We have pits and troughs in some places, and we have high points or asperities, it's sometimes called, or mountains, if you like, volcano even. And since it's the anode, this is all going to be positive. So all these positive ions here represent the fact that this is, in fact, the anode. It's a positive electrode. And the whole point about electropolishing is that the electrolyte is a very special electrolyte, and it's quite stiff, and in other words, quite viscous. It's not a free-running electrolyte, as you might imagine. And what happens is that when you start the process off, this reaction to form metal ions, it occurs preferentially at the top of the mountains. So the initial activity is very much focused on the pinnacle, the peak of the mountain, and almost nothing is happening down here. A little bit here, maybe. So what happens is, as you do this over a period of time, we start to etch away the surface of the mountains, leaving pretty much the rest of it behind. And therefore, we start to see this effect here. We have high peaks, and after a while, there are less peaks. and after a while, there are even less peaks still. And now we start to smooth out the base of these troughs. So instead of a V shape, we have a U shape. And this mountain peak's disappeared altogether here. So this is the formation of a smooth surface. It won't be completely flat. That would be idealistic. But it's going to be as close to being completely flat as we can get. And the flatter it is, the more shiny and reflective that surface is going to be in the finished object. So in a nutshell, we're going from rough to smooth, and that's the whole point of the process. But in order to do that, we need to take metal away, which goes into solution. So this is going to get a little bit thinner, as shown here. This shows the process really well, because you can see a very obvious reduction in the thickness and a very obvious increase in the shininess or the smoothness of the surface. So this picture really does show the whole process very well. Here we show it again in another context. So we now put our magnifying glass on the surface, and to start with, we have this rough, jagged edge here, and at the finish, we've taken off all the mountain peaks, and we're still left with some troughs. And the number of troughs you have left depends on how long you do the work for, how long you leave it. And you might say, well, why don't we leave it indefinitely? Well, unfortunately, if you do that, the whole object would dissolve. There won't be anything left. So if you go back to this diagram one more time, there's a trade-off between how long you do the process for in order to get a nice smooth surface and how much material you take away, leaving some still left behind to do the job. And you can see there's not much left here. They've taken most of it off by the looks of it. This has been quite heavily etched, in fact. So you have to take quite literally the rough with the smooth, if you pardon the joke there. So what else can we say about it? The workpiece is always dissolving. We're getting dissolved metal lines coming off, and we're always going to get gas bubbles off the cathode, what's called the tooled cathode. So it's the workpiece anode, the workpiece being the object we want to polish, and the cathode is known as the tool. And we're always going to get gas bubbles coming off. They may well be hydrogen gas bubbles coming off. And the power supply, the positive is always connected to the workpiece, and the negative is always connected to the tool, which is the cathode. Another thing to understand is, I mentioned a while ago that the electrolyte is not as thin as you might imagine. In fact, it's quite viscous. It's quite thick, in other words. And the mechanism which allows us to eat away the peaks of the mountains before we go into the troughs or the low parts, it can only happen if we have what's called a diffuse layer on top of the object. And this diffuse layer is actually a stationary layer. If you were to stir this in a tank, this layer, which is close on the surface, is so viscous or so thick, it doesn't move. It's what's called stagnant. So there's no convection. There's no convection in this layer here. So the only way material can go from the surface into solution is by a process of diffusion. And this diffusion process is critical in the electropolishing action. If we don't have this layer, this viscous layer, this stagnant layer, and if we do not eliminate convection in this thin layer, then the electropolishing process does not work at all. And all we're going to do is just dissolve the metal and nothing will happen. So therefore, the electrolyte is a very special electrolyte, which has to have this thick viscous layer in it, which forms on the surface. It's very thin. You can't actually see it. I haven't put the dimensions on, but it'd be some microns thick, but it won't be much more than that. It might only be a few nanometers thick. And since we're normally electropolishing a metal which has a passive film on it, such as stainless steel or aluminium or titanium for that matter, you can electropolish any of these, then there's always going to be an oxide layer on the surface as well. And this oxide layer is going to grow because we are making this anodic. And as you know, when you make something anodic, there is a tendency for the oxide film to grow. We covered this previously. If you look at the current voltage curve, it's going to look a bit like this. Imagine this is stainless steel. If you drive it in the anodic direction, you're going to start getting pitting formed if you hold the potential between here and here. And what we actually want to do in stainless steel, we want to put it into the passive region. So we need to polarize it sufficiently to get into that region. But in the case of this particular type of electrolyte, instead of just making a passive film, what we're actually doing is we're polishing it, electropolishing it to be exact. And we want to operate the potential in this flat region here. If we do that, we will get a nice surface finish. If we only hold it down here, not high enough potential, we're just going to get pits in the material and nothing's going to work properly. And if you go too high in potential, we're going to start getting too much gas evolution. And that gas evolution will take place here. We want to try to avoid this reaction if we can. We're getting oxygen because that will interfere with the smoothness of the operation. And so therefore, we want to avoid operating here, and we want to avoid operating down here as well. We want to be in the middle region. So we need to have some careful control over the electrode potential when we're doing this. Here's another example of showing the process I've just described. And this diagram here actually says viscous layer on it. It's written here. So this is the thick layer, which cannot move by convection. It's kind of stuck on the surface, almost like a glue, if you like. It's not, but so therefore the ions, the cations, can only go through here by a process of diffusion. They can't mix up. And therefore that means that therefore the diffusion length is much less for the top of a peak than it is for the bottom of a peak. So since the process is diffusion control, when the diffusion thickness is small, like it is on the top of a peak, we're going to get much more activity here than we will at the bottom of the trough, where the diffusion length is much longer. And that's why we need the viscous layer, so that the mechanism is only by diffusion and not by convection. If we were mixing all of this up and we had convection, then there wouldn't really be any difference between the peak and the trough, and we'd just wind up dissolving everything uniformly, and the surface would never get polished. So therefore, the electropolishing solution must contain this viscous layer, otherwise it's not going to work. And here's showing the whole thing again. The reason I put this on there, because I found this on YouTube, and there's a link here. If you type on that link, this is an animation, and I just got a screen capture of it, so it didn't really show it. But here you've got the rough surface to start with, and you've got this initial oxide layer, which gets removed. And here's the electrolyte polishing solution, which says here has a low electrical resistance. And of course, the oxide has a high resistance. But as we polish it, then this becomes smoother. These peaks start to disappear, and they start to match up with the troughs. If you watch the animation, you'll see the whole press going. And this shows it really nicely, showing that it uses the word eluted, but this means to be removed. The top of the peak is, because the diffusion length is not very long here, this red arrow is much shorter than the blue arrow. Therefore, we're going to attack the peak of our metal here. So this part where it's shown in red is going to dissolve faster than this blue part down here. And therefore, we're going to remove material here faster than we are here. And therefore, the process is going to result in a smoothing out of the surface. It's going to be less rough and more smooth. This shows the whole thing again in different ways. So here we have before electropolishing. This is after 15 minutes. And this is after 25 minutes. So this diagram here, this is not a very good diagram. At least it does show some time periods on it. So this is answering the question you might be saying is, how long do you have to do this for before you get the result? Most electropolishing baths or systems are designed to work quite quickly, especially if you're going to make a large number of objects, such as knives and forks and spoons. Then you want the process to be quite fast. So anywhere between 5 minutes to half an hour is typical. You probably won't go much more than 30 minutes, but you might only go for 10 minutes. And it does depend very much on the temperature. So this says 30 degrees C. In other words, it's a little bit above room temperature. And you might even go up to 60 or 70 degrees C. So the temperature is quite critical in determining the parameters which give rise to a smooth surface. and we want to have as smooth as possible. How do we do it? Well, I'm giving you a specific example here. So this example is made by a mixture of sulfuric acid and phosphoric acid mixed together, and they make quite a viscous mix. So in the lab, if you actually see concentrated sulfuric acid and concentrated phosphoric acid, they're like syrups. They're thick. They're not like water at all. In fact, you need to be very careful when you add water to this, that you add just the right amount. And the water is used to control the viscosity. But to start off with, concentrated sulfuric acid and concentrated phosphoric acid at room temperature are quite thick liquids, and therefore they give rise to this viscous mix. And the viscosity is critical in order to get the stagnant layer, which I've just described to you. And then, so you mix the two together in a certain ratio. Let's say 75% phosphoric acid and 25% sulfuric acid, for example. And you might add a little bit of water to control the viscosity. And you put it into a tank. Normally you have to heat it up. So this one has a heater in it. So let's say we're operating at 50 degrees C. Then the objects that we're going to electropolish are hung off a rack, a little bit like a coat hook. And so these are the positive. This is the positive electrode. It's connected to a power supply, which in this case is a rectifier. I'm not going to go into the details of what a rectifier is, but it's just an industrial DC power supply that gives plus and minus at high current. So all the objects are stacked here, the workpiece, the anode, if you like, and the cathodes are permanently mounted. They're part of this setup. And these might be made of carbon, they might be made of stainless steel, or they might be made of another metal, even titanium for that matter, could be. And then we do the process, and after about 10 minutes or half an hour, these will, when they're taken out and they're washed in clean water, they will have a nice shiny surface. And just to show you, here's what sulfuric acid and phosphoric look like. So it tells you they're dangerous, especially sulfuric acid. When you take sulfuric acid out of the bottle and you pour it into a beaker, you get fumes like this. It's very viscous. And as you all know, phosphoric acid in its concentrated form will react violently with water. So you must make sure that you don't put any water into this. In fact, you probably know that when you're diluting sulfuric acid down, then there's a rule of thumb here that you should never put the water in the acid. You always put the acid in the water. I'll explain to you in another video why that is the case, but you have to be careful because sulfuric acid, if you get it on your hand, it will burn the hand almost immediately because the sulfuric acid will react with the moisture in your hand and burn it. This person should be wearing gloves, but I think they've done this on purpose to show the danger. Phosphoric acid on the hand is much safer than that. If you get a small amount of phosphoric acid on your hand, it's not going to burn it. But nonetheless, you need to be careful. It's nowhere near as dangerous as sulfuric acid, but nonetheless, you have to be somewhat careful with it. So that's the end of the actual lecture for electroplating. I'm going to stop sharing for one moment and just keep the recording going. I'm putting my camera on now. So I don't know whether you can see here, but I've actually got a piece of metal that I've electropolished. I don't know whether you can see this, but somebody say if you can see that.
We can see it.
Yeah, well, can you see, I've shown you this before because the other end has pits in it where I pitted it. I showed you this a few weeks ago, but now the other end of my specimen, this is a piece of stainless steel. And the middle part looks quite grey and normal. This is the normal surface here. And this end is the end that I've electropolished. And if I waggle it around like this, you can see it shining in the light, hopefully. Can you see that's got a shiny surface on it?
Yeah.
Yeah, on both sides as well. This is about 10 minutes. Yeah, it's like a mirror finish on this side. This is really, I'm really proud of this because I did it myself. I think I'll try and make a video of how I did this. So this was done, it's about 10 or 15 minutes in the bath I made, which is a phosphoric acid sulfuric acid mix. I did it in the lab the way I've just shown you. And if you look carefully, you can see it, you can feel, if I put my finger across here, the joint, I can just feel a difference in thickness as I run my finger across here, because the base material, which has been above the electrolyte surface, this is the middle part here, this part here, is a little bit thicker than the part I've electropolished. And if I run my finger across there, I can feel a step up there, because some of the metals dissolve to give the electropolishing effect. But I think you have to agree that's really nice.